Section 5 is about the energy changes in reaction. When a chemical reaction happens, most of the time we have energy change. This energy change which happens during a chemical reaction can be in different format. But the most common format of energy change is heat change when the chemical reaction happens. For example, when you burn the fuel, you know that a lot of heat energy releases. So always with any chemical reaction, we have energy change. Energy change, as I said, can be in different format. For example, in the photosynthesis, the plant for making sugar, it needs the sunlight. So again, in this reaction, in the photosynthesis, we have the energy change, but in the form of the light. The plant takes the energy from the sunlight to make the products which are sugar. So always we have energy change in chemical reaction, but the most common form of energy change in chemical reaction is the heat. So we want to focus our study on the heat change during the chemical reactions. Based on the heat change in the chemical reaction, we have two types of the reactions, or we can divide the reactions into two main groups. Some of the reactions are called exothermic, the other type of the reaction are called endothermic. Exo and endo are the Latin words. Exo means out, so the exo means out, and endo means in. So when we say something is exothermal, means the heat energy. Okay? So exothermic, it means the heat energy goes out from the system. Endothermic, it means the energy goes into the system. So in the other word, in the exothermic reaction, energy is given out. So exothermic reactions give out energy. So there is a temperature rise. So when you burn the fuel, for example, the energy is given out from the reactants and the temperature increases. Some example of the exothermic reactions are shown here in your book. So look at picture A. The start of reaction between the iron and sulfur. So this is the reaction between the iron Fe and sulfur S. When these two react with each other, they convert to iron to sulfide FeS. And you can see a lot of heat energy produces here. Also, in this reaction, you can see that the light energy is produced. So, by reacting iron with the sulfur, the energy is given out. So, this reaction is exothermic. And if you touch this test tube, you can feel that it becomes hot. It means the temperature of the container increased. So, this is the sign of exothermic reaction. Look at picture B. In picture B, you have two solutions and we are mixing the two solutions. The first solution is silver nitrate that you have here in this beaker. And in this beaker, you have sodium chloride. So this is the reaction between the silver nitrate solution and sodium chloride solution. You had this reaction in previous chapter. By mixing this solution, you can see here that some solid material forms. So this is precipitation reaction, and that solid is precipitate. The precipitate which forms here is AgCl, silver chloride, plus NaNO3, which is your solution. So for AgCl, I put the S, mean it's solid. If you mix these two solutions, and you put a thermometer inside beaker, you can see that the temperature increases here. So this means by mixing these two solutions and by happening the reaction, the energy is given out, so the temperature has increased. So this is another example of exothermic reaction. So in the exothermic reactions, when the reactants react with each other and they converting to the product, the energy is also given out. Where this energy goes to the solution that you have here. It goes to the beaker that you have here, and if you touch the beaker, the energy also goes to your hand. So you can see that the beaker is becoming hot. Another example for exothermic reaction is shown in picture C. It's when you mix the water with the lime. The lime is calcium oxide, is the common name for the calcium oxide. So calcium oxide is CaO. CaO is the solid. So in the beaker at the beginning, you had the solid calcium oxide here or lime. When you add the water to that, some calcium oxide react with the water, and if you put the thermometer inside these beaker, you can see that the temperature increases. Again, it shows you by mixing the water with the lime, the temperature rises. It means the energy is given out, and this is an example of the exothermic reaction. But the question is, where this heat comes from? We had three examples. In all of those examples, by happening the reaction, the heat energy is given out from the system. But you have very famous rule in the science. You said the energy can neither be created nor destroyed during the ordinary chemical reaction. So where this heat energy comes from, if it cannot be created? What is the source of this heat energy? Anyone knows what is the source of this heat energy?
There was energy stored in it when they react, the energy
Yeah, stored in what?
in the reactants.
Exactly, okay? So in the reactants, in the chemical bonds of the reactants, we have special type of the energy which we call chemical potential energy. So the reactants at beginning has some energy stored in their bonds and in their attractions which we have between their molecules or particles, which we call them potential chemical reaction. When these reactants converts to the product, some part of these chemical potential energy converts to the heat energy. So here we are not creating heat energy. Okay? Only some type of energy is converting to another type of energy. In this case, the chemical energy which was stored in the reactants is converting to the heat energy. And some part of energy also stores in the product. So all of the energy which was in the reactant, some of them converts to the energy which again stores in the product, and some part of that converts to the energy which can be in the form of the light or the heat. And in this case, as I said, we are studying the heat. So some part of that transfers to the heat. So that's why if you want to compare the energy level, the potential energy of the reactants and products, which one of them has higher energy and which one of them has lower energy in these specific type of the reaction in exothermic reactions?
The reactants have more energy.
Exactly, the reactant has more energy. So we have what we call energy level diagram. It's very important. It's shown here on the right side of the page. On the y-axis you have the energy, and on the x-axis you have time or the reaction process or the reaction progress. Okay, so at the beginning you have a reactant with high energy. When the reaction happens, reactant converts to the product. Products has lower energy than the reactant. It means some part of energy in the reactant is converted to another type of the energy, and that is heat energy. The difference between the energy level of the reactants and the products are the energy which is given out during chemical reaction. So if the reactant has higher energy and product has lower energy, it means more energy is given out during the chemical reaction. and the reaction is more exothermic. So this is the typical energy level diagram for an exothermic reaction. In exothermic reaction, always the energy level of the products would be smaller or lower than the energy level of the reactants, because some energy which was stored in the reactants converts to heat energy. Look at this equation which is written here. It relates to picture A. Iron reacts with the sulfur to give you FeS. We said this reaction is exothermic. So the energy change during this reaction was negative 100 kilojoule. You know that the unit for the energy is joule, but because here we have a lot of energy, we show them by kilojoule most of the time. But what this minus sign represents here? Any idea what this minus?
Energy is given
Energy
out.
cancelled.
Yes.
Yeah, it means the energy is given out. So it means iron reacts with the sulfur and it converts to FeS, and 100 kilojoule of the energy releases during this reaction. So the minus sign shows that the energy is given out, or it is the sign of an exothermic reaction. Some example of exothermic reactions are given here. Neutralization reaction, most of the time, is an exothermic reaction. When you mix acid and the base, they neutralize each other and the energy is given out. So if you mix acid and the base, you can feel that the solution or the beaker which this reaction happened inside that is its temperature is increasing. So neutralization reaction of acids by alkalis. Alkalis means base. The famous example of exothermic reaction is combustion of the fuels. By burning the fuels, a lot of heat energy releases there, and we can use that for warming our house, for cooking, and so on. The next example is respiration. The respiration is opposite of the photosynthesis. In the respiration, the energy releases from the reactant, and that energy is used for warming our body, for movement, and also to keep the heart and lungs working. So these are examples of the exothermic reaction. Now let's move on to talk about the endothermic reaction. As I have told you, endothermic reactions take in energy from the surrounding. So again, we are not creating energy here. The endothermic reaction actually takes its energy from the surrounding. What is the surrounding? Surrounding is anything which is around the reactants. So endothermic reactions take the energy from the surrounding, and the surrounding is anything other than the reactant. It can be the solution which reaction happens inside that. It can be the beaker which the reaction happens inside that. So it takes the energy from all of them. Look at these famous example in picture D. It's the reaction of the barium hydroxide with ammonium chloride. Barium hydroxide is BaOH2. Ammonium chloride is NH4Cl. With these two substances react with each other, they take the energy from the surrounding. In this picture, you can see that you have a brick. They pour some water here on the brick, and they put the beaker on that, and then the reaction happened inside that beaker. Because the reaction is endothermic, it takes the energy from the surrounding. It takes the energy from the beaker itself. It takes the energy from the water which is under the beaker. It also, if it needs more energy, it can take the energy from the air that you have here. It can take the energy from your hand, which is here, or from the brick. So anyways, these reactants take the energy from their surrounding for the reaction to happen. This reaction is such an endothermic reaction that the water which here freezes. It means a lot of energy is taken from the water, and if you take the energy from the surrounding like the water, its temperature decreases, its temperature reaches to lower than 0 degrees, so the water there freeze. In picture E, another example of endothermic reaction is shown. It's the sherbet. Sherbet is two type of the acid. It's citric acid. Sorry, it's citric acid plus a base, sodium hydrogen carbonate. This is acid, this is the base. When these two react with each other, a neutralization reaction happens. But this type of neutralization reaction is endothermic. It's very uncommon because most of the neutralization reaction are exothermic. But these two specific acid and bases, citric acid and sodium hydrogen carbonate, they are endothermic. Their neutralization reaction is endothermic. So where the energy they take from? They take the energy from the tongue. So when you eat the sherbet, you feel that your tongue becomes cold. Another example of the endothermic reaction is shown here. Inside this crucible, you had calcium carbonate. Calcium carbonate is CaCO3. It's solid. You can decompose calcium carbonate to calcium oxide and carbon dioxide. Decomposition reaction is breaking up a substance. So if the reactant is break up to two or more substances, we say it is decomposition reaction. So in this reaction, calcium carbonate decomposes to calcium oxide and carbon dioxide. But this reaction is endothermic, so it needs to take the energy for happening. So that's why you can see that the energy is given to these substance, to the calcium carbonate, to decompose them to calcium oxide and carbon dioxide. So in all of these reactions, the reactant take the energy from the surrounding to convert to the products. That's why it's written reactants plus energy gives you the product. Okay. For how it was for exothermic reaction, in the exothermic reaction at the left side you had reactant, at the right side you had product plus energy, where that energy releases in the product side. But for endothermic reaction, reactant needs the energy to convert to products. So which one of these reactants or products has higher energy? Obviously the products will have higher
The
energy.
products.
Yeah, the product has higher energy, and this energy, the heat energy which gone into the reactant, will stored in the chemical bonds of the product. So this is energy level diagram for an endothermic reaction. You can see the energy level of the reactants is lower than the energy level of the products. It means some energy is given to the reactant. So this difference is energy taken in from the surrounding. So you know how much energy is taken from the surrounding. The reaction for picture F is shown here is decomposition reaction. Calcium carbonate converts to CaO and CO2. So the energy change is positive 178. So here you have the plus sign. The plus sign shows that the energy is taken in. So the plus sign is used for endothermic reaction. So how the question comes in the exam, for example, they can give you this reaction with the energy change, and they ask you to write down the energy level diagram. So you must know, because it has the plus sign, the reaction is endothermic and the energy level of the products are more than the reactants. Some examples of endothermic reactions are given here. So the reactions that take place in cooking. The reactions that take place in the cooking. When you want to cook your food needs to take in the energy. For example, when you cook the meat, the proteins inside the meat must be denatured to be edible. So for denaturing the protein, the energy is needed. So the cooking is an example of endothermic reaction. Another example for Endothermic reaction is a photosynthesis, but in the photosynthesis, the energy which is taken in is in the form of the light, so it's sunlight. Okay, at the bottom of the page, I have several questions. These questions are for homework. I will put the homework in the school system so you can upload your homeworks there. Let's move on to section 2. The section 2, it explains what actually happens during the exothermic or endothermic reaction. When the reaction happens, the bond between the reactants are broken and the new bond forms in the product side. Okay. So this reaction which is shown here is the reaction of H2 hydrogen molecule plus Cl2, and it converts to, in the product side you have HCl. So how this reaction happens? This reaction happens first by breaking the bond between the reactants. So in the reactants, the bond between the two atoms of hydrogen is being broken. The bond between the two chlorine atoms is being broken. When the bonds are broken, the atom rearrange, a new bond forms. So you can see on the product side, new bond has formed between the hydrogen and chloride. But for the breaking bond, you need the energy. So the breaking bond is endothermic reaction. You need the energy here. So for breaking bond, the energy must be taken in. But when the bond forms in the product side, it releases the energy. So forming bond is exothermic reaction, and forming bond energy releases. The reaction is exothermic and endothermic. It depends on these two steps. If the energy which releases by forming the bond in the product side is more than energy needed for breaking the bond in the reactant side, the energy which releases, overall the reaction releases the energy and the reaction is exothermic. Okay, so it says if the energy taken in to break the bonds is less than the energy released in making bonds, the reaction is exothermic. So in all of the reactions, at the beginning, the bond between the reactants must be broken. If the energy taken in for breaking bond is less than the energy released in making the bond, the reaction is exothermic. So always in the chemical reaction, you need the energy to break the bond between the reactants, and by forming the bond in the product side, the energy is released. So if the reaction is exothermic or endothermic, depends which one of them is more. If the energy which is taken in for breaking the bond is less than the energy which is released for making the bond, the reaction would be exothermic. Otherwise, the reaction is endothermic. These reaction which I have explained, H2 plus Cl2 gives you HCl, is shown here. You have chlorine gas inside this balloon, and the hydrogen gas is bubbled inside into the balloon. The reaction between the hydrogen and chlorine happens, and it puts the thermometer here inside it. You can see that the temperature increases, which shows the reaction is exothermic. Example 2 shows an endothermic reaction. This reaction is breaking up ammonia to its element, to N2 and H2. The balance equation is you need 2 ammonia and 3 for hydrogen. Anyways, look at this picture that you have here. On the reactant side, the bond between the nitrogen and hydrogen are being broken. They rearrange. The new bond forms between the hydrogen and hydrogen and the nitrogen and nitrogen in the product side. For breaking the bond in the ammonia, you need the energy, so the energy must taken in this step. Forming the bond releases the energy, so this step releases the energy. But the energy which you need for breaking the bond here is more than the energy which releases here. So the reaction is overall endothermic. The reaction needs to take in energy. And as it mentioned here, if the energy taken in to break the bond is greater than the energy released by making the bond, the reaction is endothermic. So if the reaction is endothermic or exothermic depends on the relative bond energy of the reactant and the product. The bond energy for the several bonds are shown here. For example, for hydrogen, single bond hydrogen is 436 kilojoule per mole. I will explain what the mole means. And when you want to find the bond energy, you must know if you have the single bond, double bond, or triple bond. For example, for the carbon, you can have carbon, single bond carbon. The energy of this bond is 346. But the carbon, double bond carbon, the energy of this bond is 612. What this means, it means if the carbon forms the double bond with another carbon, 612 kilojoule of energy releases. Or if you want to break the carbon double bond carbon, this bond, you need 612 kilojoule of energy. Another example, for example, here NH. Look at the bond between the nitrogen and hydrogen. If bond between the nitrogen and hydrogen forms, it releases 391 kilojoule of energy. If this bond, you want to break this bond, you need this amount of energy. So breaking the bond is endothermic. The energy must be given to the system, and forming the bond is exothermic. The bond forms and the system releases the energy. But I want to talk about this letter which is shown here, this term, the mole. If you have only one bond between the hydrogen and hydrogen, the energy is very, very small and it is not detectable. So for energy to become detectable, we need a lot of bond between the hydrogen to form. That's why to the energy which releases be detectable. And the mole is the unit for the amount of substance. 1 mole of any substance means 6.02 times 10 to the power of 23 mole, 3 particle of that substance. So 1 mole of carbon, for example, it means 6.02 times 10 to the power of 23 atom of carbon. So this is very large number, very big number. It's 0.6.200000 with 21 zeros here. So you can see it's very large number. So the values which are given here is not for forming only one bond, but is for forming 6.02 times 10 to the power of 23 bonds. So if 6.02 times 10 to the power of 23 bond between the chlorine formed, 242 kilojoule of energy releases. That's why the unit of the bond energy is kilojoule per mole. It means these bond energies are not for one bond, they are for 1 mole of the bond. And how much is 1 mole of the bond? It's 6.02 times 10 to the power of 23. Just calculating the energy change in the reaction. This is very important. Okay, at least you have 1 or 2 questions in your final exam for calculating the energy change of the reactions. If any reaction is exothermic or endothermic depends on the relative amount of energy which is needed for breaking the bond of the reactant and the amount of energy which releases by forming the bonds of the product. To calculate the energy change, we can use these equation which is written here. The energy change is energy in for breaking the bond of the reactants minus the energy out which releases by the forming the bond of the product. If this value is negative, it means the reaction is exothermic, and if this value becomes positive, it means this reaction is endothermic. Let's have an example to how we can calculate the energy change, and also we want to draw the energy diagram for that one. Let's do this example which is given in your book. Is the reaction of the hydrogen molecule with the chlorine molecule to give you the hydrogen chloride, 2HCl. I rewrite these equation here. So you have the reaction between the hydrogen and chlorine molecules, and the product is HCl, and the balance equation you need 2 HCl here. The first thing that you have to do when you want to find the energy change in the reaction is to know what are the bonds there. The bond between the hydrogen and hydrogen is single bond. The bond between the chlorine molecule is again the single bond. And on the product side, you have a single bond between the hydrogen and chlorine. But because you have two molecules, I would put 2 here. So on the first step, I measure the energy in this system, the energy which is needed for breaking the bond in the reactants. So I have a bond between the hydrogen and the value is 436, so it becomes 436. I have one more bond between the chlorine, it's single bond, its value is 242 as you can see in this table, so plus 242. So the total amount of energy which you need for breaking the bond of the reactant are 678 kilojoule per mole. Now we will find the energy out, the energy which releases by forming the bond on the product side. You have a bond between the hydrogen and chlorine, it's single bond. The bond between hydrogen and chlorine is given in the table. The bond energy is 431. So by forming one bond between the hydrogen and chlorine, 431 kilojoule energy releases. But here we have two type of that bonds. So for two bonds or 2 moles of the bond, you must multiply 2 by the bond energy of the HCl, and the bond energy of HCl as it's given in this table is 431. So always the bond energies are given to you in the exam, so you don't need to memorize them. So the energy out would be 862 kilojoule per mole. Now we calculate the overall energy change in this reaction, which would be 678 energy in minus energy out 862. As you can see here, the value would be negative, and the value is given here in your book. It's negative 184 kilojoule, or we can write negative 184 kilojoule per mole. This one is more accurate because we are finding it for 1 mole of the reactants and products. Okay, this negative sign here tells you that this reaction is exothermic. So overall in this reaction, the energy is released. How we can draw the energy diagram for this one? Okay, I will draw the energy diagram here at the bottom of these calculations. Okay, on the x-axis you have time, or we can write we have reaction progress. The progress of converting reactant to the products. On the y-axis we have energy, which the unit that we use here is kilojoule per mole. Let this be energy level of the reactants. Our reactants are H2 plus Cl2. On the first step we have to break these bonds, and for breaking bonds we need the energy. So we give the energy to this one to break them up. How much energy is needed? As we have calculated here, we need 678 kilojoule of energy per mole. We don't need to write the unit here because the unit actually is given in the y-axis. So when we break the bond, we have the separated atoms from each other. Then they rearrange and they form the bond to make the HCl. But the formation of the two HCl molecules releases 862 kilojoule of energy. So it releases more energy that we needed for the first step. Okay? This value is 862 62 kilojoule per mole. So here would be the energy level of the products, which are 2 HCl. So, but what is the overall change in this reaction? The overall change in this reaction is from reactant to product. So this would be the overall change. So you can see the overall the energy of the products or the system has decreased, and the value is 184 kilojoule. You can put the negative to emphasize that the energy is released here during this reaction. So this is the energy diagram for this reaction. Let's do another example which is given in your book. It's the decomposition of the ammonia. Ammonia is NH3. We can decompose it to its element N2 and H2. We have to balance the equation when we want to determine the energy change in the chemical reaction. For balancing, we need to put 2 here and 3 here. Now everything is balanced. Let's draw the molecules to know what are the bonds in the reactants and the product. We had in previous chapter the structure of the ammonia molecule. 3 hydrogens are connected to the nitrogen. You have 2 of these molecules, and on the product side you have N2 molecule, which is nitrogen triple bond nitrogen, and you have 3 hydrogen molecule, which is hydrogen single bond hydrogen. So let's calculate the energy which are needed for breaking the bond on the reactant. The bond that we have here is the single bond between the nitrogen and hydrogen. The bond energy is given in the table. The NH bond is 391. But how many bonds do we have? In each ammonia molecule, you have 3 bonds between the nitrogen and hydrogen. But because you have 2 ammonia molecules, the total NH bond is 6. So it becomes 6 times bond energy, which is 391. It is 2346 kilojoule per mole. And also we calculate the energy out, the energy which releases by forming the product. You have 1 triple bond between the 2 nitrogen. We'll look at the table to find that one. Here the triple bond between the nitrogen is 946. So by forming this bond, 946 kilojoule of energy releases. And also you have 3 hydrogen single bond. So 3 to the bond energy of the hydrogen, which is given here, is 436. So 3 times 436. It is 2254 kilojoule per mole. So the overall energy change is energy in minus energy out, which is 2346 minus 2254, which will be positive 92 kilojoule per mole. So here the overall energy change becomes positive, and this plus sign shows that the reaction is endothermic. Let's draw the energy diagram. For that, I will draw the energy diagram here on the right side of the screen. So you have y-axis, which is energy, and its unit is kilojoule per mole, and on the x-axis you have reaction progress. Let's here be the energy level of the reactant. We have 2 NH3. For breaking the bond in the ammonia molecule, we need 2346 kilojoule of energy. So we need 2036 2346 kilojoule of energy to break the bond and convert it to the atom. Then the atom rearranges, a new bond forms in the product side, which releases 2254 kilojoule of energy. So after this, the energy which is released is 2254. You can see the less energy is released than the energy we needed for the breaking the bond. So the energy level of the product would be higher than the energy level of the reactant. Here we have N2 and 3 H2 molecules. So if you compare the energy level of the products and reactants, you can see that the products have higher energy by 92 kilojoule per mole. This is the energy diagram for the reaction of decomposition of NH3. So let's go back to your book. These are written here, but some part of your textbook is not very clear what is written there because it's scrambled. So as you can see, even for the endothermic or for the exothermic reaction, which the energy overall release, you need at the beginning some amount of energy. This amount of energy is called activation energy. So it says for some reactions, not much energy is needed. Just mix the reactant at room temperature. But some exothermic reactions need heat from a Bunsen burner just to start the bonds breaking. So although this reaction is exothermic and is overall release the energy, but for starting up the reaction, you need the energy at the beginning. But you give a little amount of energy to break their bond, and then when the new bond forms, it releases more energy that we have given earlier. So the overall the reaction would be exothermic. It says, but for endothermic reaction, like the decomposition of the calcium carbonate, decomposition of the ammonia, you must continue heating until the reaction is complete. So the heat must continuously is given to the system. The questions which are given at the bottom of the page 80 is for your homework.